Hi, I'm the Amateur Logician, and in this video we're going to deal with Bernoulli differential equations. Such equations are of the general form dy dx plus p of x times y is equal to q of x times y raised to the n power. Notice that this is not a first-order linear differential equation because we have this term y raised to the n power. On the other hand, note that if n is equal to 0 or n is equal to 1, then it is a linear equation. And we know how to deal with a first-order linear differential equation. Recall that it's of the general form dy dx plus p of x times y is equal to q of x. And we can solve that equation through a so-called integrating factor, which happens to be mu is equal to e raised to the indefinite integral p of x dx. We know how to solve a first-order linear differential equation, great. But the question is, how the heck do we solve a Bernoulli differential equation? Well, we're going to do a u substitution. And essentially, through that u substitution, so to speak, we will reduce a Bernoulli differential equation down into a first-order linear differential equation. Because if we can do that, great. We can solve a Bernoulli equation. Because we know how to solve a linear equation, we will thereby be able to solve a Bernoulli equation. Oftentimes in mathematics, we take something that's mysterious or difficult or complicated, and we try to massage it or manipulate it or, so to speak, reduce it down into something that's simpler, or at least into a pattern or form that's recognizable, a form we know how to deal with. In fact, there's another type of equation. It's called a Riccati equation. A Riccati equation is a differential equation. To solve it, you reduce it into a Bernoulli equation, and then you reduce that Bernoulli equation into a linear equation. So this is a common technique, although perhaps only a differential equation fanboy could like a Riccati equation. But let's look at a Bernoulli equation. So how should we solve this? Like I said, through a u substitution. But what do we stipulate u being equal to? I think a good first step actually is to divide that equation by y raised to the n power and then see if anything pops out as a good u substitute candidate. So right now, we have dy dx plus p of x times y is equal to q of x times y raised to the n power. If we're going to divide that entire equation by y raised to the n power, that's the same exact thing as saying it's multiplied by 1 over y to the n power. So now we have dy dx y to the minus n power. That's simpler to write, so why not write it that way? Plus p of x times y raised to the 1 minus n power. Because here we have y to the first power divided by y to the n power, and of course that's just y raised to the 1 minus n power. And the right-hand side is now just q of x. It may not look like it right now, but in a minute or two it will be clear that the u substitution is staring us in the face. It's actually y raised to the 1 minus n power. And you'll see why in a couple of minutes. But we're going to move away from y land and move into u land. This also implies that we're not going to want this dy dx, we're going to want a du dx, because we want to move away from y land to move into u land, and you also will see that in u land we have a linear differential equation. So right now, let's just stipulate that u is equal to y raised to the 1 minus n power. We want to think about the derivative. The question is, what is du dx? So that would just be the quantity 1 minus n multiplied by y raised to the minus n power dy dx. If you substitute everything in, you'll enter u land, and it will be linear. That means we can solve a Bernoulli equation. But let's do this one step at a time. Right now, let's just get that u in, and then we'll worry about the dy dx and du dx after that. So now we have, or we can get, dy dx times y to the minus n power plus p of x times, not y raised to the 1 minus n power, but let's just say u, and that equals q of x. But now let's worry about the dy dx. It appears right here in this equation, so let's just solve for it. And to make things a little bit simpler or more concise, I'm going to change the notation a little bit. Instead of saying du dx, we can just say u prime. And that's perfectly legitimate. That's okay. U prime is equal to the quantity 1 minus n times y to the minus n power dy dx. Let's solve for dy dx. So we'll get u prime over the quantity 1 minus n times y to the minus n power is equal to dy dx. Great. We now have dy dx. So let's put that in there. And the y's do go away, so we're moving away totally from y land into u land. So u prime over the quantity 1 minus n times y to the minus n power times y to the minus n power over 1, the y's definitely go away, plus p of x times u is equal to q of x. Let's simplify. So we have this divided by that. Those go away. So we have u prime over 1 minus n plus p of x times u is equal to q of x. And if you look closely, this in fact is a linear equation. And so we can solve a Bernoulli equation. We can make them more explicit if you like. We can multiply that equation by the quantity 1 minus n. So that is the same thing as u prime plus the quantity 1 minus n times p of x times u is equal to the quantity 1 minus n times q of x. And again, this is clearly linear. Great. It's not that hard to solve a Bernoulli equation. But what is hard, there's no question about it, is developing that intuition that says, hey, this is a good u substitution. That's difficult. That's hard. Developing that intuition takes a lot of work, a lot of practice. There's no question about that. But besides that, this is not too bad. It's not too difficult. But let's do an example. So here I have dy dx plus y over x is equal to x squared times y squared. We want to solve for y. It is a Bernoulli equation. Let's do the same kind of thing. We will multiply that entire equation by 1 over y squared. So let's do that. So we have right now dy dx plus y over x is equal to x squared y squared. We'll multiply that entire equation by 1 over y squared. So now we can get dy dx 1 over y squared plus 1 over xy is equal to x squared. Great. We're going to do our u substitution. So what would u in this particular example be? It would have to be 1 over y, right? We can also think about this in the terms of the general equation, our general finding. So we have this u is equal to y raised to the 1 minus n power. U is equal to y raised to the 1 minus n power. So what is n in this case? Right, it's 2. So we have u is equal to y raised to the 1 minus 2. That's y to the minus 1 power, and that's the same thing as 1 over y. Great. So we have our u. But what's the derivative of that? In other words, what's du dx? So that would just be minus 1 over y squared dy dx. Great. So we have our u substitution. But let's also think in terms of this dy dx here. What's that? So let's solve dy dx in that small equation there. So dy dx would have to equal what? Minus y squared du dx. So now we can substitute that in too. So let's take that equation and make our appropriate substitutions. We have something to substitute for this dy dx, but also this 1 over y is a u. So now we can get minus y squared du dx times 1 over y squared. The y's go away. Great. So we're going to enter into u land. Plus u over x is equal to x squared. Let's simplify that. Because we have this y squared over y squared. So now we have minus du dx plus u over x is equal to x squared. This is linear, but to make this more explicit, so to speak, let's just times the entire equation by minus 1. So now we have du dx minus u over x is equal to minus x squared. Great. And this here is clearly a linear equation. So let's solve it. Remember, with a linear equation, the general form is just dy dx plus p of x times y is equal to q of x. We can solve it with our so-called integrating factor. Mu is equal to e raised to the indefinite integral p of x dx. So what's p of x in this case? It would have to be minus 1 over x. So mu is equal to e raised to the indefinite integral minus dx over x. Let's solve that integral. So that would be minus natural logarithm of x. We're not going to worry about absolute value signs. And this is an exponent. This is a logarithm. So we can, so to speak, move that minus sign. Really, it's a power, if you will. So this is the same thing as e to the natural logarithm of 1 over x. And we have inverses there, so that's just 1 over x. So mu happens to be 1 over x. Great. So let's times the equation, the entire equation, by 1 over x. So we have 1 over x multiplied by this equation. So we have du dx 1 over x minus u over x squared is equal to minus x. And by that integrating factor, the magic of it, so to speak, this left-hand side is equivalent to the derivative of the product u over x, which is really cool, because then we could anti-differentiate really simply. So let's anti-differentiate. The left-hand side is just u over x. The right-hand side is minus 1/2 x squared plus an arbitrary constant. And let's just solve for u for now. So u is equal to what? Minus 1/2 x cubed plus cx. But what does u equal? We said that u is equal to 1 over y. So let's substitute that in. So now we have 1 over y is equal to minus 1/2 x cubed plus cx. And one way to deal with this is just to times everything by y. Maybe it's kind of roundabout way to solve this, but that's all right. So 1 is equal to y times this quantity. And so therefore, y is equal to 1 over minus 1/2 x cubed plus cx. And that is our final answer. Pretty cool, not too bad. So we took the Bernoulli equation, we did an appropriate u substitution, the equation became linear, we solved it, and then we just undid, so to speak, those substitutions. So that is a Bernoulli equation.